So far in this course, we have seen two patterns for relationships between two variables. We've seen the linear pattern and the quadratic pattern. In this section, we're going to see a third type of pattern for the relationship between two variables. So the two patterns that we've seen before are displayed in our first two example tables here. So in this table, each time we go down a row, our input increases by 1, and our output increases by 5. If we want to fill in this remaining block, we'll put in 17 plus 5 is 22. And we see that each time the input increases by 1, the output increases by the same amount. Plus 5 in this case. So this is a linear function. In the next example, again, we see that each time we go down a row, the input increases by 1, but now the output increases by varying amounts. Here it increases by 1, then by 3, then by 5, then by 7. So here the output is not increasing by a constant amount, but this change in the output increases by a constant amount. So if we want to fill in this next row, we'll need to add 9. We'll have 17 plus 9 is 26 in this last row. Each time the input increases by 1, the output increases. But it increases not by a constant amount, but by an increasing amount. The way we described this pattern previously was the change in the change. Is constant. So this is the quadratic pattern that we saw in section 4.4. This next table shows a new pattern. So again, each time we go down a row, our input is increasing by 1. But now the pattern that we see is not adding the same amount to the output, but multiplying. Each time we go down a row, the output is multiplied by 2. So if we want to fill in another row, we'll fill in 48 times 2. That seems like a job for a calculator. It's 96. Each time the input increases by 1, the output is multiplied now by the same amount. Times 2 in this case. And so this then is a new kind of function. The new kind of function, of course, is the subject of this video. It's called an exponential function. In an exponential function, we have a pattern where a constant change in the input is associated with a constant factor change. And what we mean by that is we multiply by the same thing. So a constant change in the input is associated with a constant factor change in the output. We're looking at an exponential relationship. Why is it called an exponential relationship? Well, in example 2 here, we see a variable in the exponent. And let's see what the pattern in this table looks like. So when x is 1, y of x is 2 times 3 to the power 1. 3 to the power 1 is just 3. So when x is 1, y is 6. When x is 2, we have 2 times 3 to the power 2. 3 to the power 2, that means 3 times 3. So 2 times 3 is 6, times 3 is 18. When x is 3, we have 2 times 3 to the power 3. That's 2 times 3 copies of the number 3 now. We just worked this out. That's 18. And now this seems like a job for the calculator. 18 times 3 is 54. When x is 4, we have 2 times 3 to the 4th. So that's 2 times 4 copies of the number 3 now. But then this is what we worked out in the previous step. So we'll have 54 times 3 is 162. And what we see in this table is that each time we go down a row, just from the way we constructed this, we see each time we go down a row, x increases by 1, and y is multiplied by 3. So functions that can be written in the form a number times another number to the x power are going to be these exponential functions, meaning they have this pattern. And notice that we have the variable written in the exponent here. Now, The thing is that if we're going to write a variable in the exponent, we need to be able to make sense of it if we write any number we can think of in the exponent, because we can plug in any number we can think of for a variable. So right now we know how to make sense of exponents like 1, 2, 3, 4, 5. It's just that many copies of the number multiplied together. But we need more than that. We need to be able to make sense of exponent 0, of negative exponents, of fractional exponents, of any number that we can think of written in the exponent. So that's what we're going to do now. We're going to build some foundations. We're going to talk about what it means to write a negative number in the exponent, what it means to write a fraction in the exponent. In practice, we'll use a calculator for these computations. So our goal right now is to understand why this works this way, rather than just memorize the definitions. So in example 3, we're going to look at this table that we had before, right? So we just filled in this table for 2 times 3 to the x. And the values that we had were 6, 18, 54, and 162. And we can think of this as 2 times 3, which is 2 times 3 to the first power, 2 times 9, that is 2 times 3 to the second power, 2 times 27, that is 2 times 3 to the third power, and 2 times 81, that is 2 times 3 to the fourth power. And we can just confirm that I'm telling the truth about these powers of 3, right? 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. 3 to the fourth power is 81. And the reason that we're rewriting this in terms of these powers of 3 is that now we're going to look at this pattern and kind of backtrack it and say, okay, well, the previous rows then, we must have 2 times 3 to the 0, 2 times 3 to the negative 1, 2 times 3 to the negative 2, and so on. 2 times 3 to the negative 3, 2 times 3 to the negative 4. Right, so whatever goes in those previous rows should give us a hint as to what 3 to the 0 and then 3 to negative powers ought to be. Every time we go down a row in this table, we are multiplying the output by 3. Which means that when we go up a row in this table, we must have to do the opposite of that. We must have to divide the output by 3. So every time we go up a row, we have to divide by 3. So let's see what happens. Well, 6 divided by 3, that's easy. That's 2. And then after that, I think I'm going to start getting into fractions. Right? 2 divided by 3. Oh, let's just make that a fraction. So 2 divided by 3 is 2/3. And then divided by 3 again is 2/9. Divide by 3 again, we get 2/27. And divide by 3 one more time, and we get 2/81, 2/81. Okay, well, these are all 2 times the appropriate power of 3. Right, 2 obviously is 2 times 1. And then remember what's going on with the numerator in a fraction. If I have 2/3, that's 2 times a third. If I have 2/9, that's 2 times a ninth. If I have 2/27, that's 2 times a 27th. If I have 2/81, that's 2 times an 81st. And based on this pattern then, I think I see what my powers of 3 are, right? We already knew 3 to the first is 9, 3 to the second, 3 to the first is 3, 3 to the second is 9, 3 to the third is 27, 3 to the fourth is 81. But now it looks like 3 to the 0 had better be 1. 3 to the negative 1 had better be 1/3. 3 to the negative 2 had better be 1/9. 3 to the negative 4, I can count. 3 to the negative 3 had better be 1/27. 3 to the negative 4 had better be 1/81. And we notice something really neat, right? We notice this symmetry. We see 3 to the negative 1 is 1/3 to the 1. 3 to the negative 2 is 1/3 to the 2. 3 to the negative 3 is 1/3 to the 3. 3 to the negative 4 is 1/3 to the 4. And then 3 to the 0 is just kind of in the middle there, right? Taking 1/1 doesn't do anything. Taking negative 0 doesn't do anything. So 3 to the 0 being 1 also fits in with this symmetry. This gives us 2 rules, or at least shows us examples of 2 rules. A rule for what an exponent 0 means, and a rule for what negative exponents mean. The first one is simple. If we have any number that isn't 0, we raise it to the 0th power, we get 1. So 4 to the 0th power, that's 1. 2/3 to the 0th power, that's 1. 1.03 to the 0th power, that's also 1. For negative exponents, we say if I have some number to a negative power, I say 1 over the same number to the positive power. So 3 to the negative 4, that's 1/3 to the 4th. That's 1/3 3 times 3 times 3 times 3. And that works out to 1 over 81. If I have 7 to the power negative 3, that's 1 over 7 to the third. That's 1 over 7 times 7 times 7. And I'm going to work that out on the calculator. 7 times 7 times 7. That's 343. So 1 over 343. 2 to the negative 1. That's 1 over 2 to the first power. And of course, 2 to the first power is just 2. So 2 to the negative 1, that's just 1/2. Finally, negative 5 to the negative 2, that's 1 over negative 5 squared. So that's 1 over negative 5 times negative 5, which is 1 over positive 25. And of course, the calculator can handle negative exponents. So if I just directly put in 3 to the negative 4 and tell it to give me that as a fraction, that is indeed 1 over 81. 7 to the negative 3, give me that as a fraction, that is 1 over 343. 2 to the negative 1, give me that as a fraction, that is 1/2. Negative 5 to the negative 2, give me that as a fraction, that is indeed 1/25. So to actually find out these negative powers, it's totally fine to use the calculator. We just need to see what this even means and a little bit of why the pattern works this way. So now we understand positive whole numbers and also negative integers and 0 written in the exponent. So we understand all of the integers written in exponents. We don't understand fractions written in exponents, so we need to think about that. And what we're going to do is think about still this exponential pattern. And so what these fractions need to be. So here we have a table, and we're going to think y of x is 9 to the power x. So in this first row, we have 9 to the power 0, which we know is 1. In this last row, we have 9 to the power 1, which we know is 9. And we see that every time we go down a row in this table, our input increases by the same amount. So our output must be multiplied by the same amount. We need to figure out what that amount is. Well, we started with 1, and then we multiplied it by our unknown amount, and then we did it again, and we got 9. So our unknown number when we multiply it by itself has to give us 9. What number is that? Well, let's use a little trial and error. All right, 1 times 1 times 1, or I'm sorry, just 2 copies. 1 times 1, that's 1. 2 times 2, that's 4. 3 times 3, there we go, 9. So each time we go down a row here, we're multiplying by 3. In other words, 9 to the 1/2 should be 1 times 3 is 3. We see that 9 to the 1/2 should be 3 if including an x value of 1/2 is going to keep this exponential pattern. More generally, we have a word for what we're doing here, right? We're saying my unknown number squared is 9. That's just what it means to be the square root of 9. The square root of 9 is my unknown number. So for any number b to the power 1/2 should be the square root of b. In other words, the number a, such that when we square it, we get our number b. Okay, so these fractional exponents must have something to do with taking roots. What if we have a fraction that's not a half, right? Here we see another exponential pattern table, right? In the first row we're going to use y equals 8 to the x. So in the first row we have 8 to the 0, which is 1. In the last row we have 8 to the 1, which is 8. But here we see every time we go down a row in this table, our input increases by 1/3. Every time we go down a row in this table, our input increases by the same amount, so our output must be multiplied by the same amount. So we take 1 times our unknown number times another copy times a third copy. That gives us 8. So we multiply together 3 copies of our unknown number to the third power gives us 8. We'll use trial and error again, right? So 1 to the third power is 1, that's not 8. 2 to the third power, oh, there we go, that's 8. 2 to the third power is 8. So we must be multiplying by 2 every time we go down a row. It must be that 8 to the 1/3 power is 1 times 2 is 2. 8 to the 2/3 power is 2 times 2 is 4. And then 8 to the 3/3, that's 8 to the first power, is 4 times 2 is 8. We see that 8 to the 1/3 power must be 3. But again, we have a name for this. When we say what number to the third power gives us 8, we're saying what is the third root of 8. So this is the third root symbol. Notice we put the little 3 in the crook of the radical symbol. We see that any number b to the 1/3 power should be the third root of our number. In other words, the number a, that when we raise it to the third power, we get b back. And so that gives us a definition for fractional exponents, at least fractional exponents in the form 1 over something. If we have a fractional exponent in the form 1 over something, right, b to the power 1 over n means the nth root of b. That is the number that when we raise it to the nth power, we get b. So in example 8, we're just using that pattern. 3 to the 4th power is 81. That means 3 is the 4th root of 81. And so 81 to the 1/4 power must be 3. 5 to the 3rd power equals 125. That means 5 is the 3rd root of 125. So 125 to the 1/3 power must be 5. 2 to the 6th is 64. That means 2 is the 6th root of 64. So 64 to the 1/6 power must be 2. And again, the calculator works just fine for these fractional exponents. We say 81 to the power 1/4. We get 3. If your calculator is not set up to make pretty exponents, you'll need to put that fraction in parentheses. So make sure that you try this. If you're not getting 3 when you enter 81 to the 1/4 power, make sure you put the 1/4 in parentheses. 125 to the 1/3 power, we get 5. 2 to the 1/6 power. Oh no, I'm sorry. 64 to the 1/6 power. We do in fact get 2. Now, these were set up to give us, really nice numbers when we took these fractional powers. In general, things won't work out as nicely when we take fractional powers. And in fact, we'll often get irrational results when we take fractional powers. That is, we'll often get numbers that cannot be expressed as a fraction. So let's see some examples of using the calculator to calculate just any old power. So here we have 16 to the negative 3/4. I'm just going to enter that on the calculator, 16 to the negative 3/4. I get a decimal. I notice my instructions say answer as a fraction if possible. So I'm going to try to convert that to a fraction. And in this case, that works out just fine. I get 1/8. 16 to the negative 3/4 is 1/8. Next, I want to take 1/2 to the negative 7. Oh, that's easy. That's a whole number. That came out to just 128. Oh, I guess when I took the reciprocal of a half, right, that was 2. So we really just did 2 to the 7th. What about 5 to the 2/3? Oh, well, that's an ugly decimal. Let's see if we can make that into a fraction. I try to convert that to a fraction, and the calculator says no. This number can't be written as a fraction. So according to the instructions, if we can't write our number as a fraction, we'll round it to 3 decimal places. So to 3 decimal places, 2.924. Let's see. This seems weird. 10 to the power, where did this decimal come from? 1.3979. To 3, oh, that's really close to exactly 25, right? To 3 decimal places, we get 24.998. Wow. I wonder how I came up with that weird decimal. But when we take 10 to that power, we get a number that's really, really close to 25. We'll see that in 4.6. We'll see how I came up with that number. Okay, so technically speaking, we haven't said what it means to put any number in the exponent. We've said what it means to put any rational number in the exponent. But there are numbers that can't be written as a fraction. We don't know what those mean in exponents. In applications, this doesn't matter very much, but this is the sort of thing that bothers mathematicians a lot. And the way that we think about what we do next is that we're just kind of filling in the gaps in the exponential function. And one way we can understand this is by looking at the actual graph of these functions. So first we're going to look at the graph of an exponential function. First we'll make a table of values, then we'll plot points, then we'll look and see what sort of shape we're seeing. And I'm going to use the exponential pattern that we've been looking at. I'm going to fill in this 0 row and say 3 times 2 to the 0, that's 3 times 1 equals 3. And then every time I go down a row, I'll multiply by 2, right? Because I have 2 to the x. So every time I go down a row, my power of 2 is going up by 1. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. And then every time I go up a row, I have to do the opposite. I'm going to divide by 2. So 3 divided by 2, and I know I'm going to get a fraction, so I'm just going to make that a fraction. Oh, well, that's just 3/2. Divide by 2 again. I get 3/4. Divide by 2 again. I get 3/8. Okay, let's try to graph this. So I notice that I have, 4 tick marks between 0 and 2. These tick marks must be every half. So my whole number coordinates are easy, right? 0, 3, 1, 6, 2, 12, and then 3/24 is off the graph. I can't draw it, I'm just going to ignore it. Then my fractions, 3/2, so -1 3/2. That's on a tick mark still. -1 3/4, I'm just going to do my best. That's halfway between a half and 1. And then -1 3/8, that's a little bit less than a half. I'm fudging even more, but that looks okay. I'm going to make one of these points a little bit less lumpy. So what we see is this curved shape that's kind of slowly curving upward. It starts out real small. And then as x is getting bigger, y isn't just getting bigger, y is getting bigger faster and faster. As the input values get more and more negative, the output values get very small. Because we're dividing by 2. But no amount of dividing by 2 is ever going to get us all the way till 0. Right? The output on the graph will never reach 0. It'll get as small as we want, but it won't get all the way till 0. On the other hand, as the input becomes more and more positive, going off to the right, the output values get very big. right? Every time our input increases by 1, our output doubles. And so, of course, as it's getting bigger and bigger, it's never going to get to 0. So our output for a function like this, at least for this function, is never going to be 0. Let's take a look at another example and make some observations that we've had a little bit more formal. So we're going to name something called the base multiplier form. And to do that, we're going to just kind of completely naively fill in this table. So this is a table for y equals 5 times 2x. And I'm just going to plug in. We'll have 5 times 2 to the 0. Five times 2 to the 1, 5 times 2 to the 2, 5 times 2 to the 3. And I'm just going to completely naively do this on the calculator. So when x is 0, y is 5. When x is 1, y is 10. When x is 2, y is 20. When x is 3, y is 40. And the pattern here is, each time we go down a row, our output is multiplied by 2 as our input is increased by 1. So we can observe, looking at our equation, we see a 5 and a 2. We observe both of those in the table. Right, here's the 5. The 5 is the value of y. When x is 0. And here's the 2. 2 is the number that y is multiplied by each time x increases by 1. And so this gives us what's called the base multiplier form of our exponential function. In this form, we have one number times another number to the x power. The number a represents the value of the output of f when x is 0. And the number b represents the number that f is multiplied by when the input x is increased by 1. And notice that this is very similar to the slope intercept form. We had y equals mx plus b, where b was the starting value. And m was the rate of change. In other words, b was the value of y when x is 0, and m, the slope, is the amount that's added to y each time x increases by 1. One of the things we can do with the base multiplier form is to reason through an exponential function that we don't fully understand. So if we have f of x equals a times 10 to the x, if x increases from 20 to 21, that's an increase of 1. So the output is multiplied by 10. Because 10 is in the place of that b. It's the number that our output is multiplied by each time x increases by 1. On the other hand, what happens to the output value if the input value is increased by 30, or from 30 to 32? So that's an increase of plus 2. It's increasing twice. So the output is multiplied by 10, and then by 10 again. So the output is multiplied by 100. And finally, if we know that f of 0 equals 7, that means, well, when x is 0, f is 7. So a, the value of f when x is 0, is 7. This function is actually f of x equals 7 times 10 to the x. If we know the starting value and we know the multiplier, we can immediately write down the function. Next, let's think a little bit more about what these graphs of exponential functions look like. We can have increasing and decreasing exponential functions. And I'm just going to make some tables of values here. I'm just going to plug in. So 4 times 2 to the negative 2, 4 times 2 to the negative 1, 4 times 2 to the 0, 4 times 2 to the 1, 4 times 2 to the 2. And I'm just going to do that on the calculator. 4 times 2 to the negative 2. Oh, that came out to 1. To the negative 1. That came out to 2. To the 0. Of course, we get 4. To the 1, we get 8. And to the 2, we get 16. Let's see what that looks like on a graph. When x is negative 2, y is 1. When x is negative 1, y is 2. When x is 0, y is 4. When x is 1, y is 8. When x is 2, y is 16. And so we see again this curve that starts out increasing very slowly. But then as x gets bigger, y starts to increase more quickly. As x becomes a large positive number, y gets very large. As x becomes a large negative number, y gets close to 0, but doesn't get there. Right, again, y can never reach 0. Why? Well, because as we go up rows in this table, we're dividing by 2. And no amount of dividing by 2 is ever going to get us all the way to 0. Okay, this next example is similar, but instead of 4 times 2 to the x power, we have 4 times a half to the x power. So 4 times a half to the negative 2, 4 times a half to the negative 1, 4 times a half to the 0, 4 times a half to the 1, 4 times a half to the 2. And again, I could use the exponential pattern to fill these in, but for this example, I'm just going to calculate this completely naively. So 4 times a half to the negative 2. Oh, hey, that's 16 again. Weird. Oh, not that weird, right? 2 to the positive 2 is the same as a half to the negative 2, so I guess I'm not surprised. 4 times a half to the 1, that's to the negative 1 rather, is 8. 4 times a half to the 0 is 4. 4 times a half to the power 1 is 2. And 4 times a half to the power 2 is 1. So again, let's plot these points. X is negative 2, y is 16. X is negative 1, y is 8. X is 0, y is 4. X is 1, y is 2. X is 2, y is 1. So now we see a kind of similarly shaped curve, but now it's decreasing. And in fact, it's decreasing really fast at first, but then it slows down. Right, look at these two shapes together. It almost looks like they're mirror images of each other. So the first one is increasing, right? It starts out close to 0 and then gets very big. The second one is decreasing, so it starts out very big and then gets very close to 0. When x is a large positive number, we see y gets very close to 0. But again, it never quite makes it, because as x increases, we're multiplying by a half over and over again, which is going to give us very, very small numbers, but it's never going to get us all the way to 0. On the other hand, when x gets negative, we're dividing by a half, which is the same as multiplying by 2. And so negative x's are going to give us very, very big values of y. As x becomes a large negative number, y gets very large. And what makes the difference between these two is that in our first example, our multiplier was more than 1. And in the second, our multiplier was less than 1. If we have a multiplier that's more than 1, we see what's called exponential growth. So that starts out very close to 0, gets very large very fast. If we have a multiplier that's less than 1, we have what's called exponential decay. So starts out very large, gets very close to 0, and then is decreasing very slowly. Just like any other function, we can talk about x and y intercepts or an exponential, but there's a wrinkle here. Finding the y-intercept is simple. We need to find the value of y, of y when x is 0. If our function is given in base multiplier form, we can just see that. The value of y is a when x is 0. And so the y-intercept of an exponential graph is the point 0, a. That's easy. The x-intercept, though, is a problem. The x-intercepts for a function are the values of x when y is 0. But based on the patterns that we've just seen, we've seen that y is going to never be 0. Right, these are the two graphs that we found in example 13. And we saw that in one direction or the other, they get very, very close to the x-axis, but they never touch it. That shape, where a curve gets very, very close to a line, is called an asymptote. So the x-axis is what's called a horizontal asymptote for the exponential curve. And that horizontal asymptote behavior, getting very close to the x-axis but never touching it, is one of the ways that we can recognize an exponential curve. Okay, how do we actually come up with an exponential function for a situation? Well, one way we can do it is by, suppose we're given a graph, right? So suppose we're in a situation where the information that we have lends itself to making a nice graph. And we can read at least a couple of nice points on this graph. Right, looking at this graph, right, this is the point 0, 3, and this is the point 1, 6. So when x is 0, y is 3. When x is 1, y is 6. We can see that each time x increases by 1, well, what do we need to multiply 3 by in order to get 6? By 2. Every time x increases by 1, y is multiplied by 2. Let's do one more time. X increases by 1, y is multiplied by 2. And so I think that the next thing we're going to do is come up with the equation. The value of y when x is 0, that's 3. Each time x increases by 1, y is multiplied by 2. And so y equals our starting amount times the common multiplier to the x power. So we can answer some of the usual questions about functions using the table and the equation. Right, so f of 1, this is looking for the value of y when x is 1. Well, we have that in the table. When x is 1, y is 6. F of negative 1, that's looking again for the value of y when x is negative 1. We didn't happen to put negative 1 in the table, but we can use the equation. We'll say 3 times 2 to the negative 1. And I'm going to just leave that as a decimal. I don't know whether I'd rather have a decimal or a fraction. So since I have a decimal, it's a nice decimal. I don't know I need a fraction. I'll just leave it like that. If we want to say f of what is 3, we're trying to find the value of x when y is 3. Looking in the table, we see when y is 3, x is 0. So f of 0 equals 3. Similarly, if we want to say f of what is 12, we're looking for the value of x when y is 12. We find y is 12 in the table, and we see that when y is 12, x is 2. So f of 2 is 12. So working from a graph and a table, we can come up with an equation, and we can also, do the usual function stuff. Okay, so let's take these exponential relationships and actually apply them to something again. We say that two variables are exponentially related if a constant change in input is associated with a constant factor change in the output. And we can use exponential regression on our calculator to come up with an exponential equation from a table of values, even when that table of values is not in the form that would allow us to do the base multiplier form, and even when the exponential curve is not a perfect fit for the data. So here is an example where an exponential curve is not the perfect fit for the data. This is the amount of caffeine in a person's bloodstream after caffeine consumption. Can be modeled with an exponential function. So there's something about the science here that tells us that an exponential function is what we want to use to try to fit these data. So we have a data table. Whenever we're trying to come up with an equation from a data table, we start by entering the values into some lists. So we'll have 0, 1, 2, 3, 4, 5, 6 for our x values, 80, 72.3, 63.2, 55.7, 51.8, 42.4, and 40.9. And let's take a look at a scatter plot quick. So I'm going to say second stat plot, turn on my first scatter plot. The other settings are where I want them. So I'm going to say zoom stat. And I see, that curve looks a little bit bumpy. That doesn't look quite like the smooth exponential curves we've been looking at. But, the calculator will give us an equation whatever equation we ask it for. So let's see what happens when we ask the calculator to give us an exponential function. So in our calc menu, we had linreg to give us a linear function, linear regression. We had quadreg, quadratic regression, to give us a quadratic function. And now we have expreg, exponential regression, to give us an exponential function. Our x values are in L1, our y values are in L2. I'm going to go ahead and store my equation. So vars, y vars, function y1, calculate. So this gives us the equation. 80 we're told to round to 3 decimal places. 80.227 times 0.889 to the x. And we're starting to feel a little bit suspicious, right? Because we know an exact starting value, and it's not 80.227. And I bet that if I take each input value and multiply it by 0.889, I'm not going to quite get exactly the next output value. Right, so if I take 80 times 0.889, yeah, that's 71.12, right? That's not 72.3. 72.3 times 0.889, that's 64 and a bit, not 63.2, and so on. In fact, if we look at the graph of our regression equation passing through our scatter plot, we see that this is not perfectly exponential. Why would that happen? We said it's modeled with an exponential function. Well, measurements are inexact, right? It's really hard to get an exact measurement of the amount of caffeine in a person's bloodstream because, you're not going to take their entire bloodstream and filter all of the caffeine out and measure it because they need their bloodstream inside to live. So these are inexact measurements. Probably the measurements are also not taken exactly every hour, right? It's very hard to take something on the hour to like within a second or something, right? So probably the reason that this is not a perfect exponential fit is because of measurement error. That's okay. We can give interpretations to the equation. The value of A represents the starting value. This person started with about 80.227 milligrams of caffeine in their bloodstream. And we happen to know the exact starting value, which is 80. 80 milligrams of caffeine versus 80.227 milligrams of caffeine, that's pretty close. Right? I'm not going to notice 0.227 milligrams of caffeine. The value B means, right, this represents the multiplier. Every hour, the amount of caffeine is multiplied by 0.889. Now, there is a more natural way to describe this that we're going to meet in just a couple minutes. It's much more natural to describe this in terms of a percent increase or percent decrease, but that requires an extra calculation. We can use our equation to predict the amount of caffeine in the person's bloodstream after various amounts of time. So, for example, after 14 hours, how much caffeine is left in the bloodstream? That's asking us why. After 14 hours, that's telling us x equals 14. So we'll take 80, right? Y equals 80.227 times 0.889 to the power 14. And we get to one decimal place 15.5. We could also use our stored equation, right? Our calculator knows function notation. We can take y1 of 14 and to one decimal place that gives us 15.6. That's really, really close, right? 15.5 versus 15.6. I'm going to use the one from the rounded equation in giving my answer. There are about 15.5 milligrams of caffeine in the person's bloodstream. Okay, this next question is more complicated to answer, right? In this question, we're not given the value of x and asked to find y. We're given the value of y and asked to find x. So for this question, we need to solve the equation we get if we plug in 30 for y. 30 equals 80.227 times 0.889 to the x. And this is not a linear equation. We don't know how to solve this. But we know a way to solve any old equation using the intersect feature on the calculator. We're going to use the intersect feature on the calculator again to solve this equation. So I've got my stored equation in y1. I'm going to put 30 in y2. And I'm going to start by just looking at the graph with the scatter plot. And I observe I don't see a horizontal line. That must mean that my y equals 30 horizontal line doesn't show up on this graph. So maybe I'll try zoom fit. Leave the x values alone, adjust the y values so that I can see both of my graphs. That doesn't seem to help much. I can't see where these lines cross, but I can see that if I go further off to the right, I'll get them to cross. So I guess I need to adjust my window. I'm going to change my maximum X. Well, I know that the amount of caffeine has fallen to 15 in a bit by the time we're 14 hours in. So I'm going to change my X max to be 14, because I know we'll have gotten there by then. And I'm going to say zoom fit again. All right, notice my scatter plot got squished over to the side now. And now we see that our exponential curve and our horizontal line cross. To find the coordinates of the point where they cross, we're going to use that same intersect function that we used when we were working with quadratics. So we'll say second calc. We'll choose option 5, intersect. First curve defaults to the exponential. Second curve defaults to the horizontal line. And now when there's only one solution, our guess doesn't matter. We can just hit enter. And we see that the intersection is to one decimal place, x equals 8.4. Okay, now suppose just for a second that you aren't in the habit of always storing your regression equation, and you didn't store your regression equation. Well, you can type in your rounded equation. 80.227 times 0.889 to the x. So y1 equals 80.227 times 0.889 to the x. We'll keep the same y2, right, still 30. And we don't need to change the zoom on our graph because this is going to be basically the same curve. We'll just get a slightly different answer. So again, second calc, select option 5, intersect. First curve, second curve, guess. And again, to one decimal place. This is a slightly different number than we had before. But by the time we round to one decimal place, they're actually exactly the same. So using the rounded versus the unrounded equation doesn't change this answer at all. The amount of caffeine in the person's bloodstream will reach 30 milligrams after 8.4 hours. Okay, so here's another example where we're going to want to use the expreg function, even though this is an exactly exponential relationship. Suppose that you know that your table has 1 million bacteria on it as of 11 a.m. today. Also suppose that one bacterium divides into 2 every 3 hours on average. So every 3 hours, the number of bacteria will double. So 3 hours pass, the number of bacteria doubles. Another 3 hours pass, the number of bacteria doubles again. So now we have 4 million bacteria. Another 3 hours, the number of bacteria doubles again, and now we have 8 million bacteria. We can tell that this is an exactly exponential model because each time x increases by a constant amount, plus 3 in this case, y is multiplied by a constant amount. Times 2 in this case. We can tell that this is exponential, but the multiplier is not 2. Why? Because x is not increasing by 1. So we're going to use xbreg to come up with our equation because we can't directly write it down from the table. So we'll clear out our lists. We'll also clear our equations from the last problem. We'll leave that stat plot turned on because we'll want to look at this scatter plot. So our x values are 0, 3, 6, 9. Our y values are 1, 2, 4, 8. And then we want to run xbreg because we know this is an exponential function. And we'll go ahead and store our equation. And calculate. We'll get y equals 1 times, we'll round to 3 decimal places. One times 1.260 to the power x. Or we could just say, we don't need to write 1 times, right? 1.260 to the power x. And if we look at a graph, right, we still have our stat plot turned on. Say zoom stat. We see that our exponential curve with the unrounded values actually fits perfectly through all of these points. Right? This is a perfectly exponential function, even though we needed xbreg to come up with its equation. And of course, we can use this function to answer questions. Predict the number of bacteria. That's asking for y. On your desk by 11 a.m. tomorrow. X represents the hours since 11 a.m. today. So by 11 a.m. tomorrow, 24 hours will have passed. So x equals 24. Okay, so let's plug in. We'll round to the nearest whole million. Y equals 1.260 to the power 24. (1.260) to the power 24. That gives us to the nearest whole million 256. Or we can use the stored equation by saying y1 of 24 and that gives us exactly 256. Why is that such a nice number? Well, it's because 24 is a whole number of those 3-hour periods. Either way, by 11 a.m. tomorrow, our desk will contain 256 million bacteria, which is kind of a lot. Okay, one last thing to talk about. In English, we usually don't talk about what something is multiplied by. We sometimes say that some quantity has doubled, right? Or maybe tripled. But it's not normal in English to say, oh, wow, that's been multiplied by 37. Instead, especially if the multiplier is close to 1, so if something's been multiplied by 1.2 or by 0.95, it's more natural to talk about a percent increase or decrease. So let's talk about percent increase or decrease as it relates to exponential functions. So let's suppose we have the population of a small town. It was 1,250 in 2010, and then it's increased at a rate of 6% per year. So that means each year, the increase is going to be 6% of that year's population. So to find the increase on 2010, we'll take 1250 or 12,500, I can say numbers, times 6%, and we'll get 750. And so in 2011, the population is now 12,500 plus 750 is 13,250, which means the increase from 2011 to 2012 will be 6% of that. 13,250 times 6% is 795. So in 2012, the population will be 13,250 plus 795 is 14,045. All right, one more year of increase from 2012 to 2013, 14,045 times 0.06 is, now, of course, we can't actually have 842.7 people. But I'm going to carry the decimal point for the decimal place for this next step. For reasons that will become clear in a moment. So 14,045 plus 842.7 gives us 14,887.7 people as of 2013. So let's see if this really works as an exponential function. Right? Certainly we can see the starting population, which is the value of y when x is 0. That's this 12,250. Now let's see what we multiply by each year. To see what we multiply by, we'll divide. So we'll take 13,250 divided by 12,500. Is 1.06. Interesting. 14,045 divided by 13,250. Huh, 1.06 again. Um, 14,887.7 divided by 14,045. $1.06 again. That's the reason I didn't round that 0.7, by the way. Because what we see is that we actually have a common factor here. It's 1.06. And so our population as a function of the years since 2010 is y of x is 12,250 times 1.06 to the x. But how could we come up with that 1.06? I don't want to come up with the 1.06 by making a big table every time, right? How could I come up with that just from the information given? Well, it's a 6% increase. So we start with the whole population and add on another 6%, which is 106%. In other words, we start with the whole population plus 6% written as a decimal. Our multiplier is 1.06. So if we have a percent increase, we'll add it to 1. A percent decrease, of course, we'll subtract it from 1. Now we can use our equation to find the population in a later year, right? One that we didn't put into the table. So what is the population? That's asking us to find y. In 2018, so x represents the years since 2010. So x is 2018 minus 2010 is 8. We want to find y of 8 is 12,250 times 1.06 to the power 8. And to the nearest person, obviously, because we can't have fractional people. We have a population of 19,524. In 2018, the population was 19,524 people. And the last thing here just kind of sums up this relationship between the percent increase and the common factor. So this is what we saw in this example. Subtract 1 from both sides, and you get a way to go from the common factor to the percent increase. So if you found the common factor, for example, with xbreg, you can find the percent increase just by subtracting 1, and then convert to a percent. A percent decrease will subtract. So a percent increase gets added to 1, a percent decrease gets subtracted from 1. And then going in the other direction, the algebra is a little bit more complicated, but you can get the percent decrease by taking 1 minus the multiplier.